Hello students, welcome back. Let's go to section 3. This section requires some linear algebra, so I marked it as an optional topic. Historically, Math 3410 Differential Equations 1 used to require linear algebra as one of the prerequisites. Not anymore. We removed it. I mean by the faculty members of UNT Dallas Mathematics Department as a whole. Consequently, some topics became optional. But that doesn't mean those optional topics are not important. This is one of the rare topics that is still important even though optional, at least to a certain category of students, self-selected students who are going over to graduate school. Okay, so much for the introductions, and let's begin. Given homogeneous linear ODE with constant coefficients and its characteristic polynomial, we're going to define the set RQ as the set of all rational expressions, all proper rational expressions, whose denominator is the characteristic polynomial Q of S. Here, proper rational means the degree of the numerator is less than the degree of the denominator. We can prove that RQ is a linear space or a vector space. And then we are going to define EQ as the image of RQ under the Laplace inversion. It turns out EQ is also a linear space. We'll prove it too. Finally, it'll turn out that EQ is the solution space of the original homogeneous linear ODE, L of y equals to 0. We have these three claims, and we have to prove them all, and we'll do it one at a time. First, about RQ. We know that set of all real functions, or complex functions too, is a linear space with scalar field as R. Now, if it is complex function, then scalar field is C. Therefore, we don't really have to check all 9 properties of linear space. All we have to do is to establish that this is a subspace. In other words, we only have to check whether this set is closed under the linear combination. That is, K1 and arbitrary element of this RQ, R1 over Q, plus K2, R2 over Q, belongs to this RQ back again or not. That's the problem. And what was the key here? Denominator is all set as QS. The key is the degree of the numerator is less than the degree of the denominator. We have to have a proper expression. So how do we prove it? Well, here we go. K times R1 over Q plus K2 times R2 over Q. You can rewrite those as Q is the characteristic, so it goes down here like this, and it is a polynomial of degree n. And the numerator R1 is a polynomial of degree at most n minus 1. If this leading coefficient is 1, if the leading coefficient bn minus 1 is 0, then this one drops out, and then it may go down further into smaller degree, but in any case, it's not going to exceed n minus 1. Same goes here over here as well, at most n minus 1 degree. Therefore, if I take all the last terms together and introduce new characters, you see you have A's, B's, and C's, and K's. I'm running out of characters, so I'm going capital now. Some coefficient times s to the n minus first power, that's the leading term. It's not going to get any bigger than that. So again, we have to have a polynomial of degree at most n minus 1 in the numerator. So this entire expression is proper, and it belongs to RQ. So we have it. The linear combination belongs to RQ too. So it's closed on the linear combination, so it's a linear space. How about EQ? Well, it's an image under a linear map, Laplace inversion, so yeah, it's a linear space too. But let's not rely too much upon linear algebra, Math 3330. Let's do it here. Let's take the linear combination. Take an arbitrary element here, which means arbitrary elements R over S form, out of a Q form, and then take the linear combination. By the way, I'm using K's here in the previous proof, so I'd better follow the same expression here instead of getting another character, C's, and confusing you. Okay, all right. Okay, let's begin. How does it work? Take the linear combination of Laplace inversion of R1 over Q and K2 times Laplace inversion of R2 over Q, and then take those K's inside because the L inverse is linear. Then what do we have? We actually have a linear combination. Actually, I prefer this expression better than this one right here. Yeah, it's easier to read, at least, among others. Okay, and then we have linear combination of those expressions from RQ, and then we already proved this linear combination belongs to RQ. So the whole thing is a member of the image of RQ under the Laplace inversion, which is EQ by definition. So there goes the proof. Okay, now let's go to the third claim, but a brief recap. This is where we started, and then using the characteristic, we defined RQ and defined EQ as its Laplace inversion. We took kind of windy method, but in the end, what we want, of course, is the solution. We are talking about differential equations, so what we want is solution. It turns out this EQ is the solution space we are looking for. The solution space of the homogeneous linear ODE, L of y equals to 0. How does that work? Well, this is basically a reproduction of what we had been doing in chapter 2. Entire 2 weeks of work in a single viewing window, basically. Here we go. Let's begin with the original ODE, L of y equals to 0. What does that mean? That means this expression is equal to 0. Okay, we got that. And then we take the Laplace transform of both sides. Right-hand side, L of 0 is 0, so you don't really have to do anything here. And then take those coefficients out, and then we can apply the input derivative formulae, and then nth derivative becomes like that. N minus first derivative, we have similar expressions and so on and so forth. And then take the like terms together. Once you do that, then you're going to get Q of S as the coefficient expression of capital Y. And then what's left is R of S, and that has the degree of at most n minus 1. Flip this R of S to the other side, and then divide by this Q of S, and what do you have? Capital Y is R over Q, where R of S is a polynomial of degree at most n minus 1, and Q, denominator, is polynomial of degree n. So is this proper? Yes, it belongs to this. So this capital Y belongs to capital RQ. And then we want to get back to small y, so let's take Laplace inversion to get back. And what do we have? We have y belong to y EQ. That's the proof. Basically, we start from the solution, and then take the Laplace transform, do some algebra, and then Laplace inversion to come back. That's the structure of the proof. By the way, we could just take Laplace transform and then take Laplace inversion like that, because they were one-to-one. Okay, hard part is done, and then one more, basically an addendum. Is this a linear space? Well, we actually proved it already, but let's prove it again, this time directly. The solution space is a linear space. How do you do that? Again, we're going to prove that it is closed on the linear combination. So let's select two solutions, y1 and y2, which means L of y1 and L of y2 are 0. So L of y1 is 0, and L of y2 is equal to 0 as well. That's what this means. Now we want to prove that its linear combination also is a solution, which means linear combination belongs to EQ. What does that mean? We have to prove that L of the linear combination is equal to 0 as well. This is equal to 0. That's what you want to prove. So how does it work? This can be rewritten as linear combination this plus that, and we have 0 plus 0. In the end, yes, it is 0. Consequently, the linear combination belongs to the solution space too. We proved the same thing twice. This is linear space just now and also previously. But the big deal there was EQ defined in kind of windy fashion, going through RQ and then Laplace inversion and coming back. That was actually the solution space, and the proof was basically a reproduction of entire chapter 2 with some exaggeration. Okay, so much for 3.1 here. And let's mention a little bit about 3.2. The detail will be covered in a separate video. What we are going to do here is to establish the basis of RQ and EQ. Because we just proved those are linear spaces, maybe we can find bases. Indeed, the answer is yes. We can find the basis. It'll turn out the basis of RQ looks like this, where all those denominators are coming from the zeros of the characteristic polynomial. You see, characteristic polynomial can be factored completely all the way down to linear factors in complex number system if you use the fundamental theorem of algebra. You see, lambda 1, lambda 2, lambda 3, and so on, those are in general complex zeros. Some of them may be real, but there may be some complex zeros in any case. So in complex number field, everything can be factored completely down to linear factors, all right? And then M1, M2, M3, those are multiplicities. And they have to add up to total degree of n because this is nth degree. And those zeros of the characteristic polynomial, which we call the eigenvalues, will give you these functions. And deep down, the decomposition by partial fraction is hidden. In any case, we have these n functions, and those turns out to be a basis of RQ. And then, taking the Laplace inversion of each, we get the basis of EQ, which means this is the basis, this is a basis of the solution space. You see, EQ is a solution space of the original homogeneous linear ODE. So any solution of the homogeneous linear ODE, L of y equal to 0, will be represented as a linear combination of these basis functions uniquely. That's something we are going to establish in a separate video, but once you do that, then basically you get everything, you see, and any solution of the homogeneous linear ODE can be written as a linear combination of these, and vice versa. Once you have a linear combination of these, then that's the solution, and also that expression is unique, so you cannot have two different coordinates for same point given basis. So we have everything there. You can uniquely identify the solution you want. It's neat. And that's a little bit complicated, so we'll do it in a separate video. And let's do an example instead. Let's see, check the linear independence or dependence of the following sets of real functions through the direct computation. Also, identify Q of S. Okay, all right. How about this? E to the t power, e to the negative t power, t times e to the negative t power. Let's see. Let's identify Q of S first. So how am I going to get these standard basis functions? when we have, well, appropriate zeros. Let's see, we're gonna get t to the 0 power, only this one, e to the t power, so only the first one over there, so I'm gonna get only the first power. But for the other, I'm gonna get t to the 0 power and t to the first power. I'm gonna get 2, so I'm gonna get 1 power and we'll have the second power. In short, this is gonna be your characteristic polynomial. So lambda 1 is 1, lambda 2 is -1, and -1, this one has second multiplicity 2, so we have 2 of those. 0 power, 1 power. As for the proof of linear independence, tedious but not difficult. Set up a linear combination, C1 e to the negative t power, C2 e to the, e to the positive t power. Yes, this one. And C2 e to the negative t power, and t times e to the negative t power, all right. And then plug in t equals to 1, then what do you get? No, t equals to 0 first, and then this one will drop out. You get this equation, all right. Plug in t equals to 1, then this is going to be e to the 1 power, all right. And that should be e to the negative 1 power. Okay, all right. And if I plug in t equals to -1, and -1 goes over here, so that's going to be negative first power, and that's going to be positive first power, and that too is positive first power, but we have negative. Okay, all right, looks okay to me now. Sorry, there was a typo that I have to make sure. All right, now that we have a system of linear equations, 3 equations and 3 unknowns, can we solve it? Yes, you can, and it may be a bit tedious, but you can do it. Turns out we get all zeros. How about the next problem? We have e to the negative t power, all right. E to the negative t power times cosine sine. How does that thing work? Let's see. This one over here, cosine sine, are as a matter of fact linear combination of e to the 2i powers. So actually, you're going to get something like this. -1 plus 2i t, -1 minus 2i t, and this basis and that basis are equivalent because it turns out that this one can be written as e to the sine, like this, and then this one can be written as similar but minus. Oops, I forgot. Oops. Okay, all right. So these two can be written as linear combinations of these two, and vice versa. Negative t cosine of 2t can be written as 1/2 and then sum of these two. Like this. And then sine will be similar. We're going to have minus. And this is 2i. And this is minus 2i, like this. So it is possible to write these two as linear combination of those as well. So those are equivalent bases actually. As for the characteristic polynomial, you're going to have to get something like this, and the details left to the students. I'll stop here.